Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully you guys are doing well. Hopefully the test wasn't that bad. So we had a test earlier this week. And yeah, I mean, I don't really have anything else to say about it at the moment. That's going to be graded in about a week. So by early next week, you guys should know how you do on that. But for now, we're actually just going to move into a whole new topic. So let's get that started. Okay, there we go. I can see you guys and I can see the chat, so that's good. We're going to start some basic set theory today. So where we're going right now is we're going to start talking about sets and counting. And this is going to be very useful for us talking about probability, which is going to be very useful for statistics. So that's where the course is kind of going for the remainder of things. And yeah, so today we're pretty much going to talk about the very basics of set theory. Nothing too complicated. And in fact, I'll start from the very beginning and give you all the basic definitions coming up so to make sure that we're all on the same page. So, I mean, today's class and maybe going into tomorrow's class as well is going to be somewhat of an information dump kind of thing, where I'm just going to be telling you a lot of information that's going to be important. But so in terms of like examples and problems, we're not going to be doing that many, but hopefully you don't get bored because the ideas here are going to be important later on. So let's actually just, let's get into that. So the basics of set theory. And this is actually, I think it's section 7.2 in your textbook. So 7.2 sets. So we're going to talk about sets. Talk about sets of stuff. Awesome. Okay, so let's start with a bunch of definitions. Definition. What is a set? A set is an unordered collection of objects. The objects are called the members or elements of the set. And in listing the elements of a set, repetitions are ignored. So that's basically what a set is, an unordered collection of objects that we call elements or members of the set. And you can repeat them, but it actually wouldn't, the repeat would be ignored. Sets can be thought of as very general things. So we use collection and objects very generally. Right? So example, amenities at an Airbnb, right? You can think of that as a set of things. It's an unordered collection of objects. So someone can say, all right, we got Wi-Fi. Hey, we also have Wi-Fi. Hey, we have a heater. We have a TV. Now, there's no inherent order in this. And of course, you mentioning Wi-Fi twice doesn't mean you have something extra, right? You don't have 4 amenities here. You really have 3, right? So this The second Wi-Fi would be ignored. Right? Only 3 amenities. Amenities. Right? So that's like a set of things, right? So any general collection could be a set of names, a set of letters, set of objects, set of numbers, whatever, right? Let's talk about the notation. So one thing, we can name sets by letters, like uppercase letters. They're usually uppercase. And sometimes you can actually list the members inside of these squiggly brackets, right? So I can say A, B, C, D, E, F. And this listing inside curly braces is called the roster method. But you can also actually generalize this. You can say something like A, B, C, dot, 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 all the way up to F. So you can use ellipses. Ellipses to represent missing but obvious members. You can also describe what is in a set using notation like this. It's a set of all X such that, this is red such that, X is a letter of the English alphabet. Between A and F inclusive. Yeah. And this thing here is called a condition. Okay. So this is the roster method. You can use ellipses to, in case you don't want to write out all the elements and list everything, you use dot, dot, dot to represent that stuff is missing, but it's kind of obvious what they are. I've written out enough for you to kind of follow the pattern, and so we're good. Sometimes you might not be able to write down a pattern, and so you just kind of describe it either mathematically or in words or in sentences or something like that using this sort of notation. But that is it. Now, the members of the above set A are A, B, C, D, E, F. And we can express this via the notation. Something like this. I can say A, this. So this is an element of or a member of. So this is basically saying, so A is in A, right? So we can write that symbol. If it's not, if something is not a member, we write, so what's not a member of this? G would not be a member. So we can say G is not a member of A, right? So this is, G is not a member of A. Okay, so that's that notation. Yeah, let's look at a definition. Two sets, A and B, are called equal if they have precisely the same elements. That's the naive definition of equality. There are actually very high-level cases where that very intuitive definition actually breaks down and leads to all sorts of contradictions, but we won't worry about that. We're not going that far. We write A equals B in this case. So for example, if A was equal to our A, B, C, D, E, F, and B is equal to B, B, A, E, F, D, C, E, then A equals B, right? They're exactly the same set. How do I know that they're the same set? Well, what are the members of B? Well, there are little b is repeated twice, but we ignore any repeats. As far as we're concerned, there's only one little b in that set. Also, the order doesn't matter. So it doesn't matter that it's rearranged differently. It has A in it, it has B in it, it has C in it, it has D in it, it has E in it, and it has F in it. It has B and E showing up twice, but we don't care. We ignore repeats. We also ignore order, right? So these two guys, for us, they're the same set. Set is defined precisely by its members, and we define two sets to be equal whenever the members that they have are equal. Here's another definition.
What's the point of mixing up the order or adding repeats?
Because sometimes sets are used like mathematics. It's always an abstraction of some situation you see in the real world, right? So you are going to use a set to describe something in the real world. There's no guarantee that the way you as an observer observe something would be the same way someone else is going to observe it. So you might go out in nature and you might find A and then B and then C as specimens of some category, but then another scientist goes out in nature and they first come across a B, and then they come across a D, and then they come across an A. And you want to be able to say, oh, we found the same category. We're actually found the same thing. There's no telling what you would come across first. So if someone goes through and they start measuring things and building a set, different people will build a set in different ways. But at the end of the day, we want to think of these as the same thing. So it's not like we're going to be rearranging things just for the heck of it. It's just how they come to us, how we set up the problem.
Okay, thank you.
So now, talk about, there are times though, when we do want order to matter and we don't want repeats, right? So for example, and when we want that, we form what we call a tuple. People usually don't know that word, so let me write that down. Pronounced tuple. Is that how you write pole? So tuple, right? A tuple is an ordered collection of objects repetitions are not ignored. The notation for that is a coordinate, right? So like here, so regular parentheses. And this is, again, can be named by a letter or symbol, right? So this is an example of a tuple. This tuple, so this is a tuple with 6 entries, they're called. You could also say elements, but sometimes you just want to make a distinction. Also, I want you to note that T equals A, B, C, D, E, F is actually not the same as B, A, C, D, E, F. It's actually not the same as something like A, B, C, D, E, F, right? These guys are considered very different. However, if I put squiggly brackets around them, these would all be considered the same, right? It matters that the A is the first one, and the B is the second one, and the C is the third one, and so on. And the moment I switch this order, it's a different thing to me. Okay, Sebastian. It's a different thing to me, right? And if I repeat A twice, it's also a different thing. There are times when we might want this. There are times when we want repeats to count. And order to matter. So example, list of grades in a class, right? So I can say my grade G is 95, 95, 89. And the first position is test 1. The second position is test 2. The third position is the final, right? It matters that the 89 is the final, because the final counts for a bigger percentage of the overall grade than the regular tests do. It also matters that you got 95 on both tests, right? So it's not like I can just ignore the fact. Just because you scored the same score on 2 tests doesn't mean I ignore one of them. Oh, you scored the same score as the last test, I'm going to ignore this grade. Like, screw you, you don't have a test 2 grade now, right? You can't do that. This is different from, say, G equals 95, 95, 89, which really is just 95 and 89, right? So in a set, you would lose data. Data would be lost. And we cannot tell categories very well. Since if I write 95, 89, it's going to be the same as 89, 95. So which grade is which, right? Right. So this is going to be important. When we get to probability, and we're going to set up a lot of things in terms of sets. And it's going to involve us counting things that are in those sets and tuples. And there are going to be situations where we're not going to want to count repeats, but there are also going to be situations where we do want to count repeats. And knowing the difference between the two is going to be very important. And then once you do that, you're pretty much going to conceptualize what you're looking at as either a set or a tuple. And then how you count things and apply your probability rules is going to depend on whether you're applying it to sets or tuples, right? So the main thing is that sets don't care about order and they ignore repetitions, whereas tuples, they care about both of those things. So that's going to be important. What else? Let's have a lot of data here. Okay, definition. An n set is a set with n elements. An n tuple is a tuple with n entries. So, example, A equals 1, 2, 3, 7, E is a 1, 2, 3, 4, 5, a 5 set. And T equals A, B, C. I didn't want to set here. Is a 3 tuple. Okay, so that's what we would call them. Sometimes I want to identify the how many things are in there, and should I talk about that now? Also definition. Let n be an element of 0, 1, 2, 3, ... Right? So you now know what it's going to be. It could be 0, or it could be 1, or it could be 2, or it could be 3, or it could be 4, or it could be 5, or it could be 17, it could be 100, it could be 1,000, it could be 1,000,000, it could be whatever, right? It's whole counting numbers. Whole counting numbers. Then if A has n elements, we say A is a finite set. Otherwise, A is an infinite set. And let's talk about the definition. The number of elements in a set A is called the size or the cardinality of A. It is denoted absolute value of A. Or your homework might call it also N of A in your textbook. But the writing absolute values is I think, more mathematically common. So if A equals N, where N is one of these guys, then A is finite. Otherwise, we write A is infinity in absolute values, and A is infinite. Other than sets of common numbers, we will not be considering infinite sets. So that's just a heads up. Set theory can get quite complicated. It gets way more complicated when things get infinite, and very strange things happen when you start dealing with infinite sets. And if you look at the history of set theory, you realize just how serious a statement I just made. Brilliant mathematicians have literally had nervous breakdowns and ruined their mental health by studying set theory. There are people like George Cantor, which is like the father of set theory, had a lot of stuff to do with our understanding of set theory. Like when he came up with his stuff about infinite sets, it was so crazy that the mathematical community ostracized the dude, and it was like, it was not a fun life. Very modern tragedy. But yeah, we use his stuff now today all the time. You had also people like a guy called Frege, which was very instrumental in our concept of the idea of numbers, who, you know, Bertrand Russell, he actually defined numbers in terms of sets. And then Bertrand Russell, which is a very famous mathematician slash philosopher, who's famous for like, I'm gonna ruin this man's whole career with my inquisitiveness, writes him a letter and says things like, well, I really like your theory on this, but, you know, let's suppose you have a set that contains all that are not, set of all sets that are not members of themselves. It's such a set of members of themselves. And he tried to work this out with his theory, and like he had a nervous breakdown because of it. Threw his whole theory like out the window because it couldn't explain this one thing. And yeah, so set theory can get really crazy. And I mean, even today in the mathematical community, you know, set theorists they're kind of the strange group. We still love them. They're still a part of the mathematical community, but they're somewhat different in a good way. But yeah, we're not going to deal with infinite sets. I don't want to be responsible for anyone's deteriorating mental health. So we're going to keep things finite. And this includes when we get to probability, because sets can get really weird. And I am going to write down some things in a little bit that can kind of slightly hint towards that strangeness. But for now, let's actually just move on. So I can say the size of A is 5. So for example, if I have A equals A, B, C, D, E, then the size of A is 5, right? If I have something like N, this is the natural numbers, 1, 2, 3, 4, ... And by me putting ellipses at the end, it just means this pattern never ends. That means the size of N is infinity, which we're not really going to deal with a lot of sets like that, but these are just the whole counting numbers. So it's, I can mention that without too much trouble. You might notice that I included 0 here. This actually brings up a very important kind of set, which we call the empty set. And we can say the empty set because from a theoretical point of view, it is unique. There is only one thing that is the empty set. You can't have two different things that are empty sets. Like the empty set is like a concept on its own as far as sets are concerned. So the empty set is a set with no elements. It's denoted by this symbol, or more archaically by that. I'll be writing the 0 with a cross through it. Yes, okay. Another definition. We say A is a subset, or should I say a set A? We say a set A is a subset of set B if every element in A is also in B. And we write this symbol. So this says that A is a subset of B, or A is contained in B. So that's what that symbol means, kind of like a C. And this little thing down here means it's potentially equal to B. If A is a subset of B, but it is known that it cannot be equal, so it's not equal to B, then we write that with no line under it. And A is called a proper subset in this case. Here's a fact. For any set A, we have the empty set is a subset of A. So the empty set is considered a subset of any set. A subset you want to think of as a sub-collection. Think sub-collection. Right. So it turns out that you can have an empty collection, and you can have that empty collection being a sub-collection. So for example, I can look at the set of all students in this class, right? So there's a squiggly bracket, I can put all your names in it. And then I can say, I want to take a sub-collection of this set of people. I want all the people in this class who are taller, who are more than 10 feet tall. Now, of course, if I make that requirement, that fits no one, right? So the sub-collection I would have taken out of this set is an empty collection. There's no name that I would be able to put in that classification. There is no one who's more than 10 feet tall in this class, right? So that gives rise to an empty collection, right? And so we can think of that as a subset of any set. So the idea of an empty collection, the fact that we can take a collection, but come up with some impossible condition that cannot be satisfied, and hence we have an empty collection, is an idea of itself. And then you should be aware that if I have a set already and I want to make a sub-collection, the empty collection is a possibility in that case. It's always a possibility. This includes the case where A equals the empty set itself. So the empty set is a subset of every set, including of itself. Also, it's also a fact for any set A, we have A is a subset of A, because the definition of subset says every element in A is a subset of B if every element in A is also in B. But of course, every element in A is also in A, so A is a subset of A. Right? Here is another fact. Should be like an if and only if. A equals B if and only if A is a subset of B, and at the same time, B is a subset of A. So if everything that's in A is in B and everything that's B is in B is also in A, then they have exactly the same members. Let's do some quick examples, I guess, just to kind of hammer home these concepts. Example. Also notation. For not, you just put a slash. A not a subset of B. Okay, let's do some examples. If A equals, say, 1, 2, 3, 4, 5, B equals 1, 3, 5, C equals A, B, C, big C equals A, B, C, D equals 1, 3, 4, 5, 2, and E equals the empty set, then we can say that we can say things like D is a subset of A. We can also say things like D is a subset of A. We can also say things like A is not a subset of B. We can also say things like E is a subset of A. We could also say E is a subset of A. We could also say D equals A, right? Like all of these things would be valid and correct statements to make based on these examples. And you can kind of look at these and see that these things do apply, right? Notice that everything that is in B is also in A, right? There's 1, 3, and 5 in B. You have 1, 3, and 5 in A. Therefore, B is a subset of A. It is not true that A is a subset of B because, for example, the number 4 is a member of A, but it's not a member of B. So A is not a subset of B. E is a subset of A because it's the empty set. It's also a proper subset of A because we know for sure it's not equal to A. We are aware that A is not the empty set itself. D is actually equal to A. It has all the same members. It's just rearranged. We rearranged the order. So that's good. What else do I want to tell you about? Power sets. The power set of a set A is the set. It's a set, right? So I'm defining power set. I want to emphasize that it is itself a set. It's a set of all subsets of A. Set of all subsets of A. Every possible subset of A is, if you take all of those and you put those into a collection, you get what's called a power set. It is denoted by a very fancy P. So, for example, if A is equal to the set containing 1 and 2, then the power set of A would be equal to the set of all possible subsets. What are some possible subsets? These are subcollections. So one possible subcollection is the empty set. Let's not take anything from this and make a subcollection. Another possible subcollection is, well, I can take out the element 1 and throw it in a set, right? That is a subset of the original set. Everything that is in that set is also in A. I could also create a subset where I take out the subcollection 2. So I look at this collection that contains 1 and 2, and then I take 2 out and make another collection from that. That is a subset. I could also take both elements. So notice that here, our power set has 4 elements in it. These 4 elements are themselves sets. Do not forget that the empty set is itself a set. And so it's a set of sets. but it's not just a set of any sets. It's a set of the subsets of A specifically. Find the power sets of the following. So let's say B equals ABC. C equals the empty set. D equals the set containing the empty set. Just make sure that we understand the idea of what the power set is. All right, go. Someone tell me, what is the power set of B? So first of all, it is a set, but what's in it?
Like A alone, and then B alone, and C alone. A, B combined.
A alone, B alone, and these, you have to put them in squiggly brackets, C alone.
Mm-hmm.
Yeah, then?
A, B in brackets. A, C. B, C. And the empty set.
Anything else?
A, B, C.
Anything else? No, that's it, right?
Yeah.
All possible sets, subsets of B, right? So the power set of B here has 8 elements in it. Let's look at this one. What is the power set of C? C is the empty set. What are all possible sub-collections of the empty set? Can you tell me at least one subset? Give me one subset of the empty set.
The empty itself.
The empty set itself. Is there any other possible subset? Is there anything else I can take from outside the empty set to create another set? Well, no, because it has nothing in it. Like, what am I going to do? Like, I can only take the whole set itself. So that is the power set there. C, what is the power set of D? So now D is the set containing the empty set. So this set, D is not empty, but what it contains is the empty set. What are the possible subsets of D?
Could it be the empty set again, and then squiggly brackets, empty set, squiggly brackets?
Yeah, and that's it. Okay, cool. So let's actually talk about a theorem. If A equals N, right, where N is some finite number, then the power set of A, tell me how big it is. We have some examples here. So our A here was of size 2, and its power set had 4 things in it. Our B here was of size 3. Its power set had 8 things in it. Our C was of size 0. Its power set had 1 thing in it. Our D had size 1, and its power set had 2 things in it. See any pattern?
n plus 2.
N plus 2? Well, no, because this guy has 3. 3 plus 2 is 5. But we know that its power set has 8. Any other guesses? Well, the answer is 2 raised to the n. And you can actually check back on this to see that. When A was of size 2, the power set size was 2 raised to the 2, which is 4. When B is of size 3, the power set had 8. 2 to the 3 is 8. C is of size 0, 2 to the 0 is 1. D was of size 1, 2 to the 1 is 2. Turns out it's always 2 to the n. If n is a finite non-negative whole number. Okay, I can kind of talk about why, and I'm going to explain why, not because you necessarily need to know the proof, but because this is a concept that we're going to be using later on, so I just want you to start getting used to it, is that it's a matter of choice. When making a subset, we have 2 choices for any element that may be in the set. These choices are yes, included in the subset, or no, do not include it. So for example, when we had the set A, basically what we did was, you can think of this as us being a table, using a table 1 and 2. And what I'm doing is I'm looking at all possible ways that I can rearrange yeses and nos for this guy. So for 2, I can say yes or no, or yes or no. For this one, I can say yes, yes, no, no. These are all possibilities. So if I say yes to both the 1 and the 2, this leads me to the subset 1, 2. If I say yes to the 1 but no to the 2, this gives me the set with only 1 in it. If I say yes to the 2 but no to the 1, this gives me the set of only 2 in it. If I say no to both of them, this gives me the empty set. Because I'm making 2 choices for each element, I can multiply the number of choices. So we have 2 elements with 2 choices each. So we can have like this bar where we have like first element to include and second element to include. And here I have 2 choices. And here I have 2 choices. I have 2 choices for anyone. So if I have 2 choices for this guy, and for each of those choices, I have 2 choices for the next guy, then what we can do is we get 4 choices. We get 2 times 2 equals 4 total choices. The above is a counting principle, which we'll get to counting in the next section, called the multiplication rule. That's basically a rule that says if I know the number of choices for each option in a set, then the total possible types of such sets would be the product of all the options. I think that's it for now. Let me remind myself. Did I tell you guys, like I have a lot of definitions I wanted to tell you. I just want to remember. Did I tell you guys about the size or cardinality? Okay, yes. So we'll stop there for now. Have more definitions next time. And then we'd probably also go into visualizing sets with Venn diagrams. And then we move on to counting and then probability. Okay, so we'll end there. Hopefully that was clear. I mean, it wasn't really anything to figure out. It's just me giving you definitions and introducing this new world to you guys. But we'll end right there for now. Have a good rest of your day. I'll see you guys tomorrow. And yeah, see you all in the next one. Ciao.